said before, this is very, very alpha stage, what we're going to be talking about. And I'm going to pass it to Miguel.
Okay, so, as José described our, classical incident management space, one of the most important things is the diagnosis part, right? And most of you, if you are from the DevOps SRE background, you are very familiar with melt data and also Kubernetes, hopefully. Melt data is something which is quite critical for all of us that work in large-scale systems, and even the ones that are not so large-scale. We all remember adding some printfs to our code to debug, right? But at scale, we operate with vast amount of data. So typically, every company uses a melt stack. Some of them don't use traces, some of them use, but very important to have this information. So how can we know if something is happening? We need to check the metrics. That's how typically we get alerted that something's wrong. And then what is happening? How can we investigate what's the behavior of our code? Typically, we adopt two routes. Either we check the logs or we check traces, hopefully, if we have them, which are very, very important. Then we also have stack traces for profiles. That's a bit more complex. Not every company uses this. And this would be very, very easy to do during an incident if we had this architecture, right? Just a simple client application, a server that talks to a database. It would be very easy. But unfortunately, the world is not exactly like that, right? And you probably are more familiar with scenarios like this. And this is not particularly complex. So large-scale distributed systems are quite complex. They have a lot of components which produce a huge amount of melt data that we have to deal. And during an incident, some of the incidents actually span across multiple services, which makes diagnosis quite complex in real time. And time is money, right? So this pulls us back to the conversation of how are we instrumenting applications and how can we better instrument our applications to get better melt data. Typically we have a bunch of options in the market. You can, think from the Elasticsearch classical stack with ALK or FluentBit or FluentD or all of these tools that you're probably familiar with. But one of the important things, and one of the things that we see getting a lot of traction in the market is the standardization of the melt data format using OpenTelemetry. So OpenTelemetry is extremely useful for us to be able to standardize on the way that we interpret metrics, logs, and traces using the OTLP format, and it's compatible with a bunch of technologies. So that's something which is quite important for SREs nowadays. But also there's fancier ways of doing this. So eBPF, for the ones that don't know, it's based on a very old protocol called Berkeley Packet Filtering, and BPF basically allows you to. There's some echo, but I don't know. BPF allows you basically to tap into the kernel of your operating system and intercept system calls during runtime to be able to infer what kind of messages are flowing not only through the network, but also through the classical operating system calls like write and read, and fetch this information and then basically display them and surface them into a logging or metrics visualization tool like Grafana. So you'd get basically the same outcome. Of course, this has some trade-offs in terms of security. You need to have special permissions on your operating system, and it might be challenging, but it's a very good way of instrumenting code without actually having to touch your applications. So how can we leverage Agentic AI to make use of these data?
So we're just going to quickly do a very quick primer, just so we're all on the same page. Everyone is talking about Agentic AI, I know. So this will be quick. We don't have time to do a deep dive. At the end, we can try to answer questions if there's any. Maybe some of you have seen this image doing the rounds. It's quite complex. Let's focus on two aspects, the agent itself and the tools. Agents predate language models by a lot, I think like 30 years probably. But the idea is that you have an automated system, some software that has agency. It can take actions based on sensing its world and making decisions and basically iterating, right? And this new wave of agents with language models really are leveraging the language model as the brain, the thing that this says go left or go right. And we use tools to augment the LLM. So I'm not sure how many of you have tried LLMs besides just ChatGPT, just doing some code or something. But the key intuition is that LLMs are excellent at some tasks and awful at other tasks. And we can get into the weeds. So what we do is we try to build tools that leverage the strong parts and mitigate the parts where they're weak. A good example is like a calculator. Try to get language models to do math or unit conversion, it's hilarious. But if you get them to do something like named entity extraction or recognition, which is basically taking a string and understanding, okay, this word is a person, this word is a service name, this word is a time range. They excel at that. They're really good. We could already do this with machine learning, but it takes like training a model and deploying it. Now it's a commodity. We can just call OpenAI and use structured outputs or something like that, and you can do these. So really, I think the question we should ask ourselves is, why is everyone talking about agentic AI? What has changed fundamentally that caused all this hype? In my view, this is a terrible diagram, by the way, I blame Miguel, is that agents can do dynamic flow control, which is what I said before. They can take an input that's unstructured, some text, let's say an alert from PagerDuty, and they can make a decision. Should I go into the logs and look for something, or should I do something else? That's a really hard program to write. Like if you wanted to code it yourself, probably with like a ton of regexes, you could try to do something really bad. But LLMs can do this, and this is the key difference that we're seeing today. We can build systems we couldn't build before because of dynamic flow control with unstructured data. How does that tie in with what we're doing with melt data? Now, melt data is interesting for us because it's sort of the last bastion of data we want to tap into, because it's where the source of truth about the incident is happening, right? If you have an incident and you're a human responder, you're looking at the code, which we already do. You're looking at the logs, you're looking at the metrics, you're looking at traces if you have them, to really understand what's going on. So the big challenge is, like, this is a very simple diagram, but it adds a lot of complexity. The key idea is the same for logs, metrics, and traces. And it's that you have a huge, like, unmanageable amount of data. To give you a sense, Alibaba produces about 20 petabytes of traces in a day. That's crazy. I'm not sure if it's a typo in the paper, but Google produces 1,000 terabytes. So that's another one if we don't believe the first one. So really reducing that into a more manageable space is the first problem. And again, the key intuition here, think about logs. Most of the logs are repeated. Most of the traces are the same trace 1,000 times in a second. So it's how can you figure out, how can you sample the logs or the traces in a way where you're just picking the different stuff so you can understand the state of the system. And then finally, we talked about tools. We want to build the means for these automated systems to be able to navigate this search space. So that basically means I can't just simply dump all of this data into an LLM. You could try. It's probably going to be hilarious as well. But what we can do is try to do something like human responders do. Build a system that will iteratively explore the space by building an hypothesis based on what's going on, for example, in the incident room or what's in the alert. So that's the key high-level intuition about what we're building. And we are doing it in a way where we're tackling different kinds of data one at a time because they really have different challenges. We have mostly worked and tackled logs and traces. Metrics, it's still in the pipeline. And our vision is that we will have an overarching agent that can use either these tools, or they can even be agents themselves, the logs tool and the traces tool, for example, to orchestrate them and provide situational awareness. So imagine you're in an incident, and when you join, there's already a report saying, hey, we looked at the logs. This new error message isn't common. It wasn't seen before, or this trace is an outlier in terms of latency. So it's not necessarily about doing your job. It's about saving you the stress of at 3 a.m. figuring out where the log is. And like, especially if you don't own the service, it's always wonderful.
And what the problem is. So thanks. So how do we get there, right? So all of these, like all of these concerns about how can we collect data at scale, and also how can we leverage AI to be able to, parse these data, go through these data, and take conclusions about these data. We want to achieve or want to be in the path of, road to self-diagnosis. We want to be able to achieve self-diagnosis, to be able to help responders understand what's going on in, few seconds. So in order to do these, there are several strategies we need to start employing. Next slide, please, José. Thanks. So as José was explaining you, one of the main things that we're interested about is how do we reduce the search space. That's where most of the complexity is. also obviously on the navigation as well, but reducing search space is quite critical for us. And if you think about your experience as SREs and DevOps, whenever you're looking into observability data, probably the amount of time that you spend going through data that you don't really care about is quite a lot, right? And so if you think about the universe of, let's just talk about traces now. If you think about the universe of data that you have a bunch of traces that finish with no issues. Those are fine. They should be 200 green with latencies that you recognize, or at least you identify as being a normal distribution within your traffic. And then you have traces with abnormal latency, and this can be because you have a weird N+1 query that is triggered by a specific parameter that is passed on an API call, or just because you have an overwhelming load at a specific point in time of your system, right? And there's also a particular scenario where you actually have traces with errors, just because your application is misbehaving and it's returning either a 500 or a 404, whatever. 404 not necessarily, but traces with errors. And so do we really need all of these data? Probably not necessarily. So one of the techniques that we can start by employing is to just fetch a specific subset of each of these fields of this data, so that we can reason about it and have a reasonable sample to start reasoning about the problem. And this is called tail sampling, right? So once we're past that stage, well, if you think about yourself sorting an incident at 3 a.m., one of the things that you would do if you had the traces tool would be, let me look into the visuals of it and see if there's any, red dot anomalous trace, or if there is a log that says, oh, there's an error there. So you basically try to search for patterns within your melt data and try to identify where an error can be sitting, right? So one of the approaches that we're doing is we're doing trace clustering, so that we can basically aggregate clusters of traces, try to identify patterns that are different from the normal behavior of the application, so that we can better instruct the AI models to focus on a specific region. Another way, or another technique that we're looking into is trace embedding. So as you're probably very familiar with RAG techniques now, as they become quite common, is that RAGs are really good at doing semantic search, basically. So understanding that a specific word is very close to another word in an nth-dimensional matrix, just because of its meaning, not necessarily because the word is very similar in terms of the characters of the string, right? So one of the things that we can use to help our AI models looking into semantic errors, such as is there a database issue within my logs? It's to embed these logs, basically bring them into the latent space, so that we can actually perform efficient semantic search across the data. So if you think about these now, we've tried to emulate what's sort of the human workflow while diagnosing failures, but using AI, and this proves to be quite efficient. But you cannot forget that once you're also trying to solve a problem or a bug in your daily lives, you usually create hypotheses before you even start solving the problem. And you can imagine, like, whenever there's an incident call, one of the common things that happens is everyone jumps there and everyone has an opinion. Oh, should it be DNS? It's usually DNS. But so one of the things that it's very important for us as well is to establish clear fault taxonomy. This is not established by us. This is quite popular in fault tolerance research field. But there are several ways of classifying system faults in software. So fail stop and crash stops are probably the ones that are more common, when your application just randomly stops and crashes. And now with Kubernetes, hopefully it will restart back. Then you have omission, when you're actually losing messages within your distributed system, which it's a sort of a more complex scenario. Performance faults, where your application has a latency, for instance, that is not acceptable within your SLOs, or a universe of faults which is quite complex, which are Byzantine faults, basically arbitrary faults, like things that can happen which you have no idea what can be. So we want to use this fault taxonomy to be able to instruct the AI models to create plans for researching the data, right? So we propose a design that basically minimizes resource utilization by creating intermediate representations of this data, as we explained before, applying several techniques, not only the ones we've shown, but many other techniques to reduce the search space on the customer side, right? By instrumenting our applications with OpenTelemetry, making this data flow through a preprocessor that creates these smaller intermediate representations. So we're not shipping huge amounts of data outside the customer boundary, which is also very important for cost savings, and we want you to save money. So Once this data gets into PagerDuty, we will basically have our PagerDuty agent with all our smart models looking into your data. And once an incident is triggered, we're able to help responders, go through this data and provide insights about incident remediation. And yeah, time for some examples and a quick demo.
All right. So, like I said, first thing we did last year was to explore how we can use application logs. So we use Sumo Logic. I'm not sure how many of you do. And what we've implemented was essentially a system. This is in Slack. When an incident is triggered, we have a button saying analyze log errors. And it will fetch about an hour of logs for the service that's mapped to the incident. And again, you can imagine for our services, an hour of logs can be 300 megabytes of text. That would take hundreds of calls to an LLM, even today with large contexts. So we used a technique called log parsing. Essentially, it turns the logs into a template, meaning it gives you the comment structure, and the things that are variable, it replaces with a wildcard. And then a bunch of analysis on top of that before sending it to the LLM. And this would create basically groups of errors. So in this case, there's a single error for each group, but you could have multiples. And when the responder clicks on the link, he has a pre-filled link with the query for that specific logs. So it gives him like a fast track to what's going on. Now, the second one, I'm not sure you're going to be able to see it very well, so bear with me. This is a demo we did internally where we used, I'll need to pause. Are we able to read this? Well, I think so. Where we used Kubernetes data, change and event data. And what we did was build a topology of the resources in Kubernetes and understand how they were changing over time. So in Kubernetes, you can capture a lot of different stuff. For example, if a pod runs out of memory or if a policy is being violated. So this first example is actually not very good. It's just to show that it can work without false positives. It's important. In Kubernetes, stuff is always coming up and down. This video, of course, very ambitious trying to do a video. Okay, so this second example, we actually have a problem where the pod is trying to allocate more memory than it's available in the cluster. So again, all this information is available to you, but you need to scour for it. And this is something that can be done by traversing that topology log of the resources and looking at the timeline of events or changes. And finally, this is sort of the more elaborated example we built where we are leveraging the change events from GitHub. So we're looking at the PRs and we're also looking at the Kubernetes data. And what you get, so in this case, we had someone commented out a free. That's always a great idea in a C application. So what happened was the pod went into a crash loop back because of OOM. So this information is provided by Kubernetes. It knows the pod ran out of memory. But now because we're combining two types of data, we can actually say, yeah, the root cause is you've commented out that, and that's caused that's relatively simple enough for an LLM to do. Now for extra comedic factor, I'm going to try to do it a live demo, which is sure to work. I think so. So here the idea is this is the latest thing we've did, which is fully agentic system. And it is able to answer questions related to traces. This is with synthetic data. And the idea is that it could be a person interacting with the agent, or it could be another agent. And what you can see here is this idea where I'm asking questions, and these are sort of capability questions for what we would imagine a traces agent would be. You're saying, okay, does this service have latency over 200 milliseconds? First thing the agent does, it sort of plans ahead and says, okay, I first need to figure out what the storage service is. So it's going to get that from an API call. And then when it has the name, which is application Flask API storage, it's going to do a query and set the min duration to 200 milliseconds. And then it can do a count. Pretty simple. So again, you can see the idea of the tools and how they can increment the ability of a language model, which basically is not that smart, to be honest. And this is where we see an example of, wait, what? No. Live demos. Fantastic. Let's see. All right. So this is where you see an example of doing the embedding search that Miguel talked about. So in this case, it's going to fetch the traces, turn them into vectors, and then look at your query, which in this case, it's query database connection issue. And then, yep, it found one. There's a timeout due to a queue pull. So we've essentially used Locust to force this service to have a connection pull exhaustion. So out of all the traces, it can look for, is there anything semantically related to problems connecting to the database? And I think there's more examples, but I think these are the sort of relevant ones. So I think you've all had enough.
Yeah. So I guess like one of the important highlights is to think about, basically PagerDuty by leveraging the data that we retrieve and the data that we own for many, many years of incidents and understanding how incident resolution goes, postmortems, and also with code and melt data, we can actually build workflows that are quite powerful to be able to help you diagnosing problems during incidents, saving you a lot of time in terms of debugging, especially at nighttime, which is pretty bad, trust me. And yeah, that's what we had to share with you today. So thank you so much. Hope you enjoy.
Hello, everyone. First of all, I'm so glad to be here. Today, I'm going to talk with you about GitLab runners that scale as a service, or a product that is called Fleeting Runners. So basically, what I'm going to share with you today is my experience over the last almost 2 years working for an internal product for a car manufacturer that has some let me call special needs in terms of CI/CD. So yeah, let's start, and I think you will have a look. Okay, so let me put this here. So the agenda, so I will start by the problem, what we face when we started this product, so why we have this necessity, then the solution that we are working on, current challenge that we are facing with the growth of the project, and then at the end, the future of the solution. So what is our vision for the next midterm, or short term? First of all, a little bit about myself. So my name is Oliveira. I'm a senior DevOps at XGeeks. I want to thank especially Cloud Native Lisbon. We are at XGeeks, we are a consulting company more focused on Cloud Native and AI. Community is part of our DNA. We are drive by the community and by sharing our knowledge. And we are one of the organizers of Cloud Native Lisbon, along other groups. I'm a Cloud Native enthusiast, whatever that means, and I'm also more recently an OWASP Leiria chapter co-leader. First, before starting, I want just to get a feeling of the room. Who here has experience with GitLab CI? Showing my hands. Okay. Who have already the necessity to set up your own runners? Okay. And who had to manage those runners? Okay. And is anyone from GitLab itself here? No. So I can talk and I can say bullshit. That's perfect. Before we go, did anyone already got a call from PagerDuty at 4 a.m. here? I also hate these guys. Okay. So let's go. Okay, so the starting point. Working for a car manufacturing company is very difficult because, and pay attention that I'm working with the guys who are working for the infotainment system, the climate control, the autonomous driving system. So if each one of these teams has very specific and very unique characteristics or requirements. And it's very common for a team come to us saying, yeah, I know I need privilege mode is required to run my pipelines. And then the second team come to you and say, yeah, but Windows-based high resources machines are essential for our pipelines because we are using this particular tool. And then another team, our project requires specific tools and versions to be compiled. And then a fourth team, we require Zenzefi server. I don't even know what the hell is Zenzefi server, but apparently they are using it to flash some devices. and so on and so on. So containerization technology, storage is our main concern because we need to cache our dependencies. And quickly this turns into an ocean of different requirements. And managing all these requirements, it's very hard if you just rest on one team. It will require a lot of communication. You need to understand all the things that they are doing. You have different time zones. You have people in India. We have people in Germany, in the US, in Portugal. And it was defined from, or it was very clear for the beginning that we had to somehow lead the runner management. When I say runner, let me just clarify one thing, because probably some of you don't have experience with GitLab, but probably you might have experience with GitHub Actions, Jenkins, Drone CI, whatever tools. So in Jenkins, I think they are called executors, if I'm not mistaken. On other tools, they have a different term for that, or for those systems, basically, are the slaves that work and build where your pipelines build. So in GitLab, they are called runners. So runners, executors, whatever you want to call it. I think it's better to give you a similar term. So basically, this will turn into a huge amount of use cases that we cannot predict by the beginning. And it was very clear for us that just dealing or managing all these runners is not possible. So we will need to find a way to pass that ownership somehow to the teams, because they are the ones who know what they want, how they want, which version they need, and so on and so on. So the challenges in the traditional. So in the traditional is like having just a DevOps team or CI/CD team just to managing those runners. Resource inefficiency. So yeah, by default, we are humans. We don't know if 1 gigabyte is enough. So let's put 128 gigabytes just in case, because I don't want PagerDuty to call me at the middle of the night, which will lead to resource inefficiency. Scalability limits. So I can do something now that it works, but there is a peak in terms of demand, and I need to quickly act, but my team cannot be around. For example, they could be reduced by vacations and so on, which will lead to scalability limits, for example. Cost overruns, this is basically implied by the resource efficiency. You need to maintain all this infrastructure, probably it will fix. Okay, you will over-provision for sure. During the weekends, probably is not even necessary, so you need to set up some automation to turn it off. That will not work for some reason, whatever. And then, of course, at the end, there is a result for all these issues, that is delayed deployment. So at the end, you are impacting the outcome of those teams somehow. So how to handle X amount of use cases? We'll need to build, or we had to thought about building a solution that was adaptive, okay, to every use cases, knowing that we don't know all of them from the beginning. Cost effectiveness, and nowadays this is like, I think the buzzword for this year, sorry, it will be to reduce costs no matter what, especially with all the craziness around the world. Configurable by default, so you need to find a way to deliver the configuration responsibility to the teams. And dynamic product, so a dynamic that could have some capacities to scale based on demand. So nowadays, or today, I can have 10 machines, but tomorrow I can have 20. And that's how fleeting runners appear. So why fleeting? Fleeting comes from the GitLab plugin that is called Fleet. And what fleeting plugin requirements are? Basically are just two things. A runner manager that is no more than a GitLab runner with a plugin installed. A plugin that will contact or interact with your cloud provider API. And what we call executors, that basically can be just a simple virtual machine that has only 3 requirements. GitLab installed, Git GitLab installed, and wherever you need. So any kind of dependency, I don't know, like a compiler, you probably know better than me, anything that needs your code or your pipelines to run. This fleeting runner plugin, as I said, you have three for the three major cloud providers nowadays. So you have AWS, Azure, and GCP. When we start this project, was like 2 years ago. Yeah, 2 years ago. And the only provider that was in the beta, okay, it was AWS. And luckily, it's the cloud provider, or they are not just using that cloud provider, but is the cloud providing that they are using the most. So yeah, this was the selected one. At that time, if I'm not mistaken, GCP didn't exist yet, and Azure was still in alpha. So let me talk with you about the base architecture. So our product is no more than this. So you have a team, a project team or a group inside GitLab, and you need GitLab runners to it. What we provide? We provide an AWS account for each team, what we call ECUs. Inside these ECUs, we have a ECS container or ECS service, sorry, Elastic Container Service, where all the runner managers are running. So basically, at this point, the only responsibility for these runner managers are to be here running with the fleeting plugin installed, and they will register against a project or a group. It depends what the teams define. Once they receive a job, they will scale auto-scaling group, and inside that auto-scaling group, some machines will be provisioned, what we called executors. How much? I don't know. The user define. Which type? I don't know. Which operating system? I don't know. How much volume they have? It's all teams' responsibility to set up what they want here. How many? Also the teams. This basically is all being provisioned by a Terraform module. So basically, at the end, what our product is nowadays is just a Terraform module that they have to instantiate as many times as they want. That basically abstract. Yeah, I can call it this way. So basically, this Terraform module will abstract from the users or from the teams all this provisioning stuff. Like they don't know where the runner manager is. They don't know which VPC. They don't know how this AWS account is connected to the internal network. They don't even to know. They just need to say, I want a runner called my runner with the tag ABC, and I want this instance like this type of instance, and it will run like 5 parallel jobs, whatever. So basically what I just said, they can manage or they can deploy as many runners they want. So basically a runner manager is one instantiation of our module that basically corresponds to a runner with a certain tag or tags that are registered against a project or a group that will manage a specific auto-scaling group with specific types of machines. These machines, so as you saw, the second part of the fleeting plugin requirements is a machine that has GitLab runner and everything that you need. So we trust on Packer, also from HashiCorp, to do that, to build the AMIs or the Amazon Machine Images. So we have a base, what we call the base AMI, that has like the bare minimal for this to work. GitLab, matching the GitLab version that we have here and our GitLab platform version. What are we installing more? Like CloudWatch agent, Datadog agent nowadays. Some more tools that we need for our project to work, but then they can even customize their own AMIs on top of it using also Packer. On a more complicated architecture, so this is what could look like. So I have 3 random managers, each one of them managing a different autoscaler with different instances. So these ones are smaller, yeah. With different operating systems. This one also has, or is using a special executor called Docker autoscaler. So basically, the jobs don't run on the context of a machine, but on a context on a container inside that machine. They can use whatever AMI they want, and they also can have what we call storage capabilities for the ones that need to cache dependency between jobs or something like that, like S3. Nowadays, we offer S3, EFS, or Elastic File System, and FSX. In terms of compute feature sets, so for you to know what we are already able to do. Single instance or multiple type of instance. This basically is, you can just define, I need my runners to use this particular instance type, which for the majority of the people or the projects is okay. But there are some, let me call them crazy guys, that they need like instance with 1 terabyte of memory, and AWS is not able to provision you like 300 of them. So basically, there is a second option that is multiple instance types, where you can select like, this is the primary one, but if you don't have, use this one or provide me that one or that one. Cross-region deployments. So yeah, we are present in two regions so far, multiple architectures. So nowadays we are provisioning them x86 and ARM-based instance. In terms of configuration, so as I mentioned, they can select between Windows and Linux. For Windows, we have 2 versions. Yes, 2 versions, and Windows exactly the same, 2 versions. They can have multiple executor types, instance and Docker, autoscaler. So instance, what I said, an instance is spin up and the pipeline runs in the context of the instance, like SSH command. So basically, the Docker autoscaler, a Docker is spin up inside that instance, and it runs on the container context. Ephemeral, not ephemeral execution, so they can save data or not. It depends on their storage solution. Isolated or parallel environments, they can select like each job run in each instance, or I can have multiple jobs running per instance. It's their choice, guys, basically. Configurations, so customizable images. They can build their own AMIs using Packer. If not, if they don't have any requirement, we provide base images that we know that are working. Images and zombie housekeeping. So basically is when they are building their own AMIs, they are testing, they are installing this stuff, this product, this tool, and basically those AMIs are being stored there, and then we are housekeeping them or cleaning them to save costs. And cloud export images. Cloud export images is a very specific feature. So if a car manufacturer wants to be compliant with a norm called ISO 26262, I think that's the number, or is it the other way around? I never know. Each piece of software, whatever that means, must be reproducible by 15 years, if I'm not mistaken. And the runners where those pieces of softwares are built must be reproducible or rebuildable. Let's call it this way. And the runners are also part of it. So basically, these guys can extract an AMI that they use today to rebuild any deprecated software that are on a car, like within 8 years, for example. Storage and size, storage type and size. So yeah, they can set up how much volume space they want. Fast disk usage, so if they select an instance type that has NVMe support, we ensure that the NVMe disk is the used one. GitLab cache, shared network storage with those 2 options, EFS and FSX. Scalability and availability. So we are trusting on cloud to also provide us these two words, horizontal and vertical scaling. So they can say, I want 10, 20, 30 jobs per instance, or they can say, I just want one job per instance, but I want to scale up to 500 instances. Concurrency on Docker, reference kit, and best practices. So basically, this is like a knowledge base or preset of templates that they can just get and apply. And finally, in terms of feature set, observability, and FinOps. So we provide by default some observability that they can check. I will get to it later. And some cost awareness by job, where we basically, at the end of the job, they can have a prediction of how much that job costs. Monitoring out of the box. So basically, we know, and sorry for some of the blurred things, but I had to blur them. We know like how many jobs run during the last month, how much did it cost. So nowadays, we don't have all the teams already onboarded because some of them are still trusting on Jenkins. We are talking about 400K just in AWS costs nowadays. So we know how much jobs are running at the moment, how is the distribution by the different projects. And for the project itself, we also provide this kind of dashboards like pipeline overall success rate, how many executions, times, and so on. So this we trust in Datadog to provide all these kind of dashboards to the users. Some of the numbers. An issue, why not? Yeah, okay. So we are talking about nowadays about 350K of jobs per month on our runners, a job duration of 1,055K of minutes per month, 25, this was our peak, 25K jobs in parallel. No, sorry, this is what they have configured now, and this was our peak, sorry, 3K. We have more than 40 AWS accounts. We have, our users has 15K of vCPUs asked, 40 terabytes of memory, and basically, yeah, we are talking about 350K in euros. Apart from this is just the fleeting runners, okay? So inside this company, we have three types of runners, what we call shared. Shared runners is just a Kubernetes runners that can be used to linting and other stuff. They run 1.5 million jobs per month. We have fleeting runners, this solution, and we have also self-host runners for all those runners that need, I don't know, let's imagine they need a physical thing attached to a PC to test something, yeah. So this is not the entire cake, let me say this way, it's not the entire cake of the job, so this is just a small fraction. I think nowadays our market cap is like around 30% in terms of fleeting runners. Current challenges. This is my favorite part, sorry. Knowledge gap. During the last year, we onboard a lot of people, a lot of ECUs, and each team has different skills, that's for sure. And some of the teams don't know, for example, never worked with Terraform, or some of them never worked with Packer. And to be honest with you, that's kind of an issue so far, because we are facing some very simple questions that our users don't know how to work with the product. I don't want to say work with the product. At the end, they don't want to read like all the documentation, all the available inputs, and basically build their module, because they have another thing to do, or probably they don't have skills enough to do it. So this depends team to team, okay? Then inner layers dependencies. This is a pain at the moment, and we are working on this, or we will work on this for the next 3 months. Our product is like I like to say it's like an onion. It has a lot of different layers. So you have our module version, and also the base AMI version, and their custom AMI version, and the GitLab runner version also, and the GitLab platform version, and so on and so on. So there is a lot of versions somehow need to be synced. And it's not easy to do, because let's imagine one thing. I'm building this product, okay? I tested the new version of my fleeting render module with a very specific custom base AMI version, sorry. And I know that I know that it works on that. But their custom AMIs are based on top of our base AMIs, and probably they don't want to build another one. So this is quite complex to explain like in 2 minutes, but yeah, if you have some more questions at the end, I can try to explain it better. Nowadays, this is one of the issues, and we are trying to create what we call holistic versioning, where we can use a common version to all of the things, whatever that means. And FinOps with meaning. So nowadays we have some feedback, okay, in terms of cost. So we said, okay, this job that you had here running for the last 6 hours had an estimated cost of 100 euros. Doesn't matter. But that doesn't say anything nowadays, right? Is it, okay, what should I do? So our idea in the future is to grab that data, check their current utilization, and basically advise them to make changes on their current configuration, like use a less powerful machine because you don't need, or during the weekends you don't need at all. So try to scale down your fleeting runners to 0 during the weekends, because you don't need this instance to be there running and spending money. So basically this is just working with the current data and turn what they called FinOps with meaning. So basically identify opportunities and optimizations. About the future of the solution, I think I'm already burned all my time, sorry. Quickly go. Okay, so this is the vision, and this is what we want to achieve more or less at the end of this year. So nowadays our project is poorly based on an infrastructure as code or infrastructure as service-based solution, where they have to manage their Terraform code, where they have to manage the Packer code. So we are already abstracting all the stuff about infrastructure and AWS accounts and so on, but we want to abstract even further. So we want to create another abstraction layer called Runner Management Platform. And we already have something like that, like a POC that we built for the last weeks. That basically is no more than a front end, data front end with all the options available, but through a wizard. Like through a wizard, and you select, okay, I want this this field is required, this is not required, and they basically at the end they fill all the things that they need, and the Terraform module definition is already provided to them. But you want to go even further, all the things that I have talked so far to fight those challenges. Images management platform is also, this is like in our minds nowadays, we don't know how to do it yet, but it's also to abstract the Packer layer. For example, if I know that there are 2 or 3 or 4 teams that are working with Android Auto, I can set up some scripts, like a Play Store for scripts, to install some tools, and they just could like include on their Packer, like a store. Let's call it the store. So basically, this is what we want to achieve at the future, is a product-based solution. They don't need to take care of Terraform. What is under the hood? They just need to say, I want this runner this way, and please deploy it. It's your stuff to do it. And that's it. Thank you so much. I would love your questions if you have any. If not, we can also talk during the pizza. Are the pizzas here? Okay, so we are ready to go. Thank you, guys.